welcome to the second video of bipolar junction transistor. In this video, we will learn about the need of junction biasing for BJT. In the last class, we have seen that the construction of BJT, it has three regions and two junctions. Under the unbiased condition, the only depletion layer is formed across each junction and there is no use of bipolar junction transistor. For the suitable operation of BJT, a DC voltage source needs to be connected across each junction. When a DC voltage source is applied across emitter, base and collector terminal of a bipolar junction transistor is called biasing. From onwards, we will consider NPN transistor for the analysis. This is because in NPN transistor, electrons are treated as majority charge carrier and the mobility of electron is faster than hole. That is why the NPN transistor is considered. Since bipolar junction transistor is a three-terminal two-junction semiconductor device. To operate the BJT in desirable region, it is necessary to bias each junction properly. In this figure, it is seen that the each junctions connected by a battery source. So when we connect the battery across each junctions, there are four various ways of connecting the battery. Let us suppose the both junctions may be forward bias, both junctions may be reverse bias. When emitter based junction is forward bias, in that same time the collector based junction is reverse bias. When the collector emitter based junction is reverse bias, in the same time collector based junctions may be forward bias. Consider the first case when emitter based junction is forward bias and collector based junction is reverse bias. To make this emitter based junction forward bias, it is necessary to connect the base terminal by a battery source of positive potential to the base and negative terminal by the emitter by a voltage source VEB. To make this collector junction reverse bias, you need to connect the collector terminal by a positive potential of the battery and base by a negative potential of the battery by a voltage source VCB. In this case, a bipolar junction transistor is used as an amplifier. Now consider the second case. In this case, both junction is forward bias. To make both junction forward bias, the P side or the base terminal connected by a positive potential of the battery and emitter terminal is connected by a negative terminal of the battery by a voltage source VEB. To make this junction reverse forward bias, this collector junction needs to be connected by a negative potential of the battery and the base terminal is connected by a positive potential of the battery by a voltage source VCB. Now, in this case, the bipolar junction transistor is act as a on switch. Now consider the third case. In this case, base emitter junction is reverse bias. To make this junction reverse bias, base terminal is connected to the negative potential of the battery and emitter terminal is connected to the positive potential of the battery by a voltage source VEB. In the same time, the collector base junction is reverse bias. To make this collector base junction reverse bias, this collector side needs to be connected by a positive potential of the battery and base side connected to the negative potential of the battery by a voltage source VCB. The fourth condition, base emitter junction is reverse bias and collector junction is reverse bias. This biasing arrangement is not used because in this case emitter is act like a collector and collector is act like an emitter. In this case, sometimes the transistor may destroy. Now consider the PNP transistor. Here it has two junctions and three terminals. To operate the PNP junction transistor in proper biasing arrangement, we have to follow the same conditions. Emitter based junction is forward bias. So emitter terminal is connected to the positive potential of the battery and base terminal is connected to the negative potential of the battery by a voltage source VEB. In the same time, the collector junction is reverse bias. To make this collector junction reverse bias, this needs to be connected by a negative potential of the battery and this is connected to the positive potential of the battery by a voltage source VCB. In this case, the PNP transistor can act like an amplifier. The second condition, both junction is forward biased. So to make this base emitter junction forward biased, this emitter terminal is connected to the positive potential of the battery and the base terminal connected to the negative potential of the battery by a voltage source VEB. To make this junction forward biased, this collector side needs to be connected by a positive potential of the battery and base side connected to the negative potential of the battery by a voltage source VCB. In this case, transistor is act like a on switch. Now coming to the third case. In this case, base emitter junction is reverse biased. To make this base emitter junction reverse biased, this P side is connected to the negative potential of the battery and N side is connected to the positive potential of the battery by a voltage source VCB. In the same time, the collector junction is reverse biased. To make this junction collector reverse bias, this P side is connected to the negative potential of the battery and base side connected to the positive potential of the battery by a voltage source VCB. In this case, the bipolar junction transistor can act like a off switch. Now, coming to the various current components in a bipolar junction transistor. This is the general symbol of bipolar junction transistor. Here, the arrowhead at the emitter side indicates the type of transistor. If the arrowhead going outward at the emitter junction, it is called NPN transistor. In this figure, there are various current components are seen. The current that is flowing through the base terminal is known as base current. The current which is flowing through the collector terminal known as collector current. The current which is flowing through the emitter terminal is known as emitter current. In this figure, if we apply the KCL at any point, it is seen that emitter current is equals to summation of base current and the collector current. Since the base current is very small, IB is very small, so it can be neglected and thus the emitter current can be approximated to collector. In this figure, the PNP transistor symbol has been shown. If the arrowhead is going inward at the emitter terminal, this transistor is known as PNP transistor. Here the various current component is showing that current which is flowing through the base is known as base current. The current which is flowing through the collector side terminal is known as collector current. The current which is flowing through the emitter terminal is known as emitter current. In this case also, the emitter current is equals to base current plus collector current. Since base current is very small, so emitter current can be approximated to collector current. Now consider the various voltage component across the PNP or NPN transistor. Here, before going ahead, I would like to suggest every operation or every component of a transistor can be assumed when the transistor is operated into active mode. To operate this transistor into active mode, it is necessary through base emitter junction forward bias. So to operate this junction forward bias, the base terminal is connected to the positive potential of the battery and emitter terminal is connected to the negative potential of the battery. To make this collector junction reverse bias, so this collector terminal is connected to the positive potential of the battery and emitter terminal is connected to the negative potential of the battery. Here, this voltage is designated as voltage between base and emitter. This voltage is designated as voltage between collector and emitter. The various current component flowing across the NPN bipolar transistor, IB is known as the base current, IC is known as the collector current, and IE is known as the emitter current. This is the now come to the polarity of each terminal. Here the collector terminal is connected to the positive potential of the battery and emitter terminal is connected to the negative potential of the battery. So this side is connected to the positive potential of the battery, and this side is connected to the negative potential of the battery, and the voltage drop between collector and base is designated as VCB. If we apply the KVL in this direction, VCE minus VCB minus VBE is equals to 0. So VCE is equals to VCB plus VBE. In the same way, here it is the image of PNP transistor. To operate this transistor into active region, because to analyze any transistor it is necessary to operate each transistor in active region. So here it is a PNP transistor. To operate this transistor into operate active region, this base emitter junction should be forward biased. To make this junction forward biased, this N side or base side is connected to the negative potential of the battery, and this emitter side needs to be connected by a positive potential of the battery by a voltage source VBE. This collector junction is reverse bias. Since the collector side is made up of p-type material, so it is connected to the negative potential of the battery, and this emitter side is connected to the positive potential of the battery by the voltage source VEC. This terminal is the collector terminal and connected by negative potential of the battery, and this is connected by a positive potential battery, and the voltage drop across collector is designated as VCB. Now if we apply the KVL in whole system, then minus VEC plus VCB plus VBE is equals to 0. So VEC is equals to VCB plus VBE. So this is the general equation for measuring the voltage across each terminal. Here it has been assumed that the value of VBE is remain constant, because we are going to use the silicon transistor. For silicon transistor, the value of VBE is always assumed by 0.7 volt, and the value of VBE for germanium transistor it always be assumed as 0.3 volt. Thanks for watching the video.